It is section 8.5. In this section, we'll study methods and issues on cluster validation. For supervised classification, we have a variety of measures to evaluate how good our model is. For example, accuracy, precision, and recall can be used. For these two, we haven't defined them yet. We'll define them soon. For cluster analysis, the another question is how to evaluate the goodness of the resulting clusters. Because we don't use labels, it's not easy to answer the question. The clusters are in the eyes of the beholder, which means that clustering is quite subjective. Yet we want to evaluate them. There are some reasons. We want to avoid finding patterns in noise. This pattern from noise is useless. So we have to distinguish them and now discard. And also we want to compare clustering algorithms. If you make more than one set of clusters, then we want to compare the sets of clusters. And also we can compare two clusters. Here we have aspects of cluster validation. We have to understand the clustering tendency of the data set so that we can distinguish non-random structures from all the retrieved. That means that random structures from clustering algorithms must be ignored. Now, for validation methods, you may try to here do external validation and or internal validation. External validation means that using some externally known labels, ground truth labels. So once it is known, then that is quite easy. Now, for internal validation, we are using all the data so that it's not so simple. Now, also we want to compare clusterings to determine which is better. And also, we should determine the correct number of clusters. Through cluster validation, also we can choose correct number of clusters. Okay, here we'll define precision and recall. Precision is the fraction of relevant instances among all the retrieved, while recall is the fraction of relevant instances that were retrieved. If we read this definition, it's not really clear. So here we'll see an illustration. I copied this picture from Wikipedia. Okay, so for data set, whole data set, for information retrieval, it may include relevant elements and non-relevant elements. And the retrieval result can be here combined from relevant side and non-relevant side. And so that this whole thing is now retrieved elements. Here, for that one, the question is, how many retrieved items are relevant? So that among all retrieved, the portion of true positives, that is the relevant element is called precision. So try to look at the picture. And now the question is, how many relevant items are retrieved? That means that from all relevant elements, we try to measure the portion here retrieved. So that is called recall. It's a really good illustration in Wikipedia. So I put here. And therefore, both precision and recall are about relevance of the retrieval, measured respectively from all the retrieved instances and all the relevant instances in the database. So along with this note, and you can understand the precision and recall more precisely. Okay. Now we'll go back to cluster validity. Here we have measures. For external measures, now we are using ground truth labels. Here, that is now, here the examples are entropy, purity, and rand index. And precision and recall also can be used. Here we'll consider later entropy and purity. Okay, for internal measures, now these measures are used to measure the goodness of the clustering structure without respect to external information. So here, correlation, similarity metric, and sum of squared error SSE and silhouette coefficient. And we'll go through these examples. Now also, you may use relative measures. And now they are used to compare two different clusterings or clusters. And often an external or internal measure is used for this relative measure. For example, SSE or entropy can be used. Okay, here we'll define correlation, coefficients rho xy between two random variables x and y with the mean values mu x and mu y and standard deviations sigma x and sigma y. The correlation between two random variables x and y is defined in this way. Rho xy is now covariance of xy over now sigma x times sigma y. The value will be between -1 to 1. Now, if x, y, and y are independent, then the correlation coefficients must be 0, but the reverse may not be true. Now, that is a definition of correlation between two random variables. Now, for two vectors u and v, we can define correlation in this way. That is exactly cosine. The correlation is exactly that is cosine. Dot product divided by the product of their norms. So that's exactly cosine. Now, the correlation between two matrices can be defined similarly by considering the matrices as vectors. For two-dimensional array, the matrices, and we consider that as one elongated vectors, and then try to measure the cosine, then that is exactly the correlation between two matrices. That is definition. Okay, here we want to measure cluster validity via correlation. Okay. And so we need two matrices. One is a proximity metric, P, and the other one is incident metric, I. Here, proximity metric means that point by point, you may measure similarity or dissimilarity, so that the metric must be capital M by capital N. Capital N is the number of points. So point-wise distance will make, for example, here, similarity metric. That is a kind of a proximity metric. And incident metric, it can be made in this way. Now, point-wisely, for each pair of points, once they are in the same cluster, then the position is 1, and if not, then the value is 0. In this way, incident metric will be made. Okay. Of course, they are symmetric, so that here you can compute only the half of that. For example, upper the triangular portion can be computed, and the other part can be copied. Okay. And high correlation indicates that points that belong to the same cluster are close to each other. Now here, one is the distance measure. The other one is now the index, so that if you try to measure the correlation, then that must be true. For example, for k-means clustering of two data sets, here one is now well separated data set, and the other one is now not well. But along with k-means, here now along with k3, the 3 clusters are made. For this clustering, here now try to measure correlation, then that is around 1 in modulus. And for this data set, here the value is far from 1 in modulus. Okay. But this, the correlation is not a good measure for some density-based or contiguity-based clusters. Now, another application of using similarity metric is here. Okay, we order the similarity metric with respect to the cluster labels and inspect the visually. That is the strategy. And that means that we order points, for example, for these points in the same cluster, now we order start from 0 and order that. And then now for this point, we order here, so that here the point will be ordered class by class, the cluster by class, and attached in now stacked in lower row-wise stacked. Then now the similarity metric itself will show such graph. Look at over there. Now that is around 1 between inside of the cluster. And of course, over there, if you are measuring distance itself, then that will be small, and the other area large. But it's a scaled or reciprocal can be measured, so that you can see here in the same class it is large, and for different class points that is small. So that here now you can see very crisp similarity metric. Okay. For this data set here, DB-scan is made such kind of here clustering, clusters, and look at over there. Now there is the largest one here. Now there is a second largest one. It's a small cluster, and you can see here the pattern. Now for k-means is relatively same number of points are selected for each cluster. You can see here from over there, there's one class, another one, now another one, right? Okay. Now that is a result from k-means, and there is a similarity metric visualized. And along with now the complete linkage hierarchical clustering method case, it has such a three clusters. Now here it's not so much criticism. Of course, over there, the three methods are not so crisp, which means that the clustering result is not so quite clear. And depending on your opinion, and some result must be discarded. Okay. Now for this data set, here DB-scan is used, and here now the similarity metric is relatively quite crisp, so that DB-scan is working very nicely for this data set. Okay. This is end of the part 1. We'll continue in the second part. Thank you.